Hello everyone, you're tuned into today's PIR live event and I'm your host Scott Jones. Our guest today is Dr. John Smol, who's a professor in the Department of Biology at Queen's University and a Canada Research Chair in Environmental Change, also an officer of the Order of Canada. Welcome to the PIR live event, Dr. Smol.
Oh, delighted to be here. Thank you.
So before we get started today, I'd also like to welcome the viewers who are watching our live stream. It's great to have you with us as always. Remember that anytime during the half an hour, you can tweet us your questions using the hashtag AskPIR. If there's room in your tweet, please include your name, school, or city, and I'll give you a shout out. So I look forward to getting to those questions. In the meantime, I'll turn it over to Dr. Smol, who's going to tell us a bit about his background and then talk about his work. So thank you for joining us, Dr. Smol.
Oh, a pleasure to be here. Well, what I wanted to talk about today in a brief introduction is what climate change is all about and the problems with greenhouse gas emissions. And I was asked to also focus a bit on the work that I do in my lab here at Queen's University. And some of the work we do is in the Canadian Arctic, in fact, the high Arctic. So I thought I would just talk a little bit about that. And hopefully you see my slides. The slide here I have is just a picture of our planet Earth, a picture you're probably all familiar with. I think there's two things to notice, or two or three things to notice about this picture. One, it tends to be bluish, and that's because most of the planet is in fact water. If, as others have noted, if alien beings ever came to this planet and they gave it a name, they wouldn't call it Earth, they'd probably call it water. And that water is very important. Without water, there would not be life to start with. And very critical that water is fundamental to life, and it's also fundamental to many of the processes we talk about with climate change. Another thing you would see is that if you looked at this carefully, much of the earth and water has a greenish tinge to it. And that's because of plant life or photosynthesis. And this, of course, drives much of the ecosystems we have. And finally, you don't actually see it when you look at a picture of the earth, but surrounding the earth is a very thin atmosphere. And that's really what we want to talk a bit about here today. It's quite thin. People say, it's 30 different lengths. But usually if you have a globe sitting on your desk, like these globes, the thickness of the atmosphere that we're talking about here today is probably the thickness of like the coating on the globe. That's how thin it actually is. So we're dealing with a relatively small part of the atmosphere. Not a very, very, very thick layer is what I wanted to say. And we have, as human beings, we have been changing that atmosphere around us by releasing greenhouse gases, especially carbon dioxide, but other gases, methane and so forth. And that has been changing how heat is kept on this planet. And we often refer to that as the greenhouse effect. And I have one schematic in the next slide here that's, I think, a simplified version of what we actually have to worry about. The ultimate source of energy, of course, on the planet is the sun. And the sun, that's what keeps the planet from being totally frozen. We get heat coming in from the sun. And some of that energy comes down to and hits our planet. Some of it along the way is reflected, things like clouds and other material. But a certain amount of energy is always coming in and hitting planet Earth. That comes in as what we call shortwave radiation, but it also, after it goes back up into the atmosphere by long-wave radiation. It's reflected, it's radiated back out. And I think if you can feel that if you're ever on a hot August day on a parking lot, and you put your hands on that black parking lot material, you can feel sort of heat coming out of it. And that's the heat going back out from the Earth. Now, before we started changing the atmosphere with greenhouse gases, everything was more or less in balance, the heat coming in, the heat going out. What happens is what we call the greenhouse effect is we've added more of these greenhouse gases. We've always had greenhouse gases, a certain amount, and they're important. If we didn't have them, the Earth would be frozen. So it's good we have some. But we've been adding more greenhouse gases, and that's been trapping some of that heat. And that's what the real issue is. We've been changing the atmosphere by burning coal, burning oil, all these fossil fuels. That has increased the amount of greenhouse gases, and it's not letting some of the heat escape. So there's a simplified version of what the problem is. Now, I was asked to talk about the Arctic here. The Arctic is in the northern regions. One reason is because I work in the Arctic. That's a good reason, probably. The second reason, the Arctic is especially sensitive for climate change. You often hear of the Arctic and the Antarctic as like the miners' canaries of the planet. They're the first to show signs of climate change and other types of climate change, and often to the greatest degree. And this schematic kind of shows it. You see how much warming is expected, and I think you can see the Arctic regions in the north here are especially sensitive, going to be showing the biggest changes. So what's the reasons for that? Well, there's several reasons, but one of the most simplest ones is the Arctic has what we call high albedo. That's a big word for saying reflective, or mirror-like would be another one, or white-like. And what do we mean? We mean typically the Arctic is full of ice and full of snow, and that's white. And that reflects. It's like a mirror. It reflects heat. And I use this analogy. I picked this car off the web, this picture off the web, but I have a white car and a dark car. And if you went on a hot August day in the parking lot in front of your school, you put your hand on each of those cars, they'd both be hot, but the black car would be hotter. That's because the black car has low albedo or low reflectivity. The white car is more like the Arctic in its natural state. The white car is more like a mirror. It's reflecting heat. It's another reason why we might wear white clothes in summer, to reflect heat. Well, the problem is if you start warming the planet, you lose some of that whiteness. You lose some of that albedo. You lose the mirror, if you like, and it goes more from going from the white car to more like the black car. You're going from, and I'll show you this in, it's something like going from, instead of having snow and ice, you're exposing earth, rocks, and non-ice covered oceans and lakes. Those are going to have the lower reflectivity. They're going to absorb more heat. So everything happens much faster in the Arctic, partly because of this albedo. And we also talk about feedbacks. And the Earth tends to try and has a variety of mechanisms to get itself back into equilibrium. And we deal with this all the time. For example, in your house, you would have a thermostat. That keeps your house warm in winter and cool in summer. And that's considered a negative feedback. A negative feedback means that it's bringing it back. So what happens when your house gets cold? The thermostat kicks in and tells the furnace to go back on and bring it up to a certain temperature. And then once it gets a certain temperature, it turns off the furnace. In some way, the air conditioner would be doing the reverse. That's like a negative feedback. This sort of diagram here just shows you what's actually happening as a positive feedback. And this is typically what's happening in the Arctic, why it's so sensitive. So here, if we warm the planet by increasing greenhouse gases, if we cool we haven't warmed the planet yet. Say in a typical scenario, we start off by cooling the planet. It increases the amount of snow and ice cover. That increases the so-called albedo. It makes it whiter, and therefore it decreases temperature. More of the heat is being reflected back into the atmosphere. If, however, with greenhouse gases we warm the temperature, that decreases the snow and ice cover. That decreases the reflectivity, and you warm the temperature. You warm the temperature, you get less ice and snow cover. So you can see how this becomes a feedback system. So the more you warm it, the more you lose the ice and snow cover, the more it warms, and this is why things happen very quickly in the Arctic. Now, you might ask, well, who cares about the Arctic? And some people do say that. The problem is we live in Canada, and the issue is that about half, depending on how you define the Arctic, but about half our landmass is in the Arctic and about 2/3 of our coastline. So we're an Arctic country, whether we might recognize it or not. So I'm going to show you where I've done some of my work, and I'm just going to show you in a very preliminary way what we've done. But I live down here in Kingston, Ontario, and it's gotten quite a bit easier to get to the Arctic. I've been doing this for 30 years. It wasn't always quite so easy, but now all I have to do is I have to get myself to Ottawa, which is about a 2-hour drive. Now you can take a jet, a 727 jet or whatever, right to Iqaluit, the capital of Nunavut. That goes every day. You can go every day easily. It's about 4 hours on a jet. Then you stay in Iqaluit a bit. Then you take a much smaller plane, and that's a much smaller plane. That's usually 4 or 5 hours, and you go as far as Resolute Bay. That's the last commercial airport. Then you take a much smaller plane, and you go about 3 or 4 hours to Alexander Fjord, and quite often you land on the sea ice because there's no airports anymore up here. Then you go by helicopter, and then you walk. So what I'm saying is some of this work is hard to get to, but I'm going to show you the examples of some work in the very high Arctic up here, about 80 degrees north, approximately 80 degrees north. So it's very high up in the Canadian Arctic. And this just shows you how you do that last bit. I said you take a small plane. This is in Resolute Bay. First of all, this picture is taken in June, and I think you can see how much snow is still in the background when this photograph at least was taken. Now, it's less snow now with warming. But this is called a Twin Otter. That's one of the main planes we use. It's very hard to get to some of these sites. And I don't know how well you see on your screen, but you see these big, what we call tundra tires, big balloon tires. But you'll also see skis. It has both skis and tires. Because in Resolute Bay, we're going to take off on wheels, but by the time we get to our sites on Ellesmere, we'll be landing on skis because we're going so much farther north even than this. But that's really one of the main ways we get to these regions. And when it comes to summer, the summer is still very short in these regions. You know, you're still wearing sweaters and jackets even in July and August. And for example, here's an Arctic hare. Two things I wanted to show you here. First, the animals have not seen humans, so they're not scared of them. You can come right up to pretty well any animal. They're not scared of you. Second, this little guy here, that's a pretty good camouflage for winter when it's snow and ice, which is, you know, most of the year. But you can see during the summer, he's not too well disguised here, but yet seems to have no fear. But that's the type of animals you have. Now, I work on lakes, and I'm just going to give you a few shots to close this talk about how we work on lakes. And we often refer to the Arctic as a natural laboratory. That's because it's relatively untouched. We can do the same things I'm going to talk about in the Arctic down in Ontario or southern Quebec or wherever we are. But it's complicated because we have roads, we have agriculture, we have a lot of other things affecting the ecosystem. Up here we have far less, so it's much simpler in many ways to do this kind of work. And one of the things that the Arctic, as I've sort of been telling you, is characterized by lots of snow and ice, or at least it's a natural state. This is what the lakes, what the oceans look like. And again, you appreciate what I was saying with the reflectivity. It's like a big mirror. So as long as that ice and snow stays, we're in pretty good shape. The problem is the ice and snow with the warming is decreasing. And here's one picture of how that's affecting lakes. You know, on the top I have here what maybe this lake looked like in the 1800s when it was significantly colder, then it's slowly beginning warmer and warmer. And now in summer, many of these lakes have no ice cover at all. They're completely open. And you can see the albedo where the reflectivity is changing. So things are changing very quickly in this region. Now, you may ask, how do I know what the temperature was like in the 1800s? How do I know what it was like in the 1700s? We don't know directly. No one was measuring temperature. You know, no one with thermometers was walking around the Arctic in the 17 or 1800s. What we do is we use indirect methods. And by that, that's my field of research. Basically, I use lakes. I'm interested in what happens in a lake and what happened in the history of the lake. And if you think at the bottom of a lake, it's like a time machine. Slowly, lake sediments, mud at the bottom of a lake slowly accumulates over time. They're constantly, mud is coming down and it's accumulating at the bottom. That's like a time machine. The deeper you go, the older it is. We can go back thousands of years. It's just slowly accumulating information over time. And so what we look at is we look at the material that's coming from fossils, from organisms that live in the lake, with material coming outside the lake. And what we do is we remove a history book. That mud layer is like a history book at the bottom of a lake. And what we use is these types of cores. This is a core, this is from Ontario, but this is taking a history book of the lake. As I go deeper, it's older in order. That'd be about, say around here is the 1800s. This would be about the 1700s. This would be about the 1600s. We have ways of measuring that. This is a simple mechanism here, but if I show you this, it's basically, this is all it is, and we lower it down into the sediment, and then we send a messenger down, and it stops the top here. I use the analogy. It's much like if you had a milkshake in front of you, and you took a straw. And you took a core of your milkshake, because the surface sediment is much like a milkshake. It's very, very watery, very loose. So if you have a milkshake and you want to take a core of your milkshake, you put a straw into the milkshake, then you put your thumb on top of the straw, and you pull it up, and you'd have a core of your milkshake, basically. We're doing kind of the same thing here. It goes down with this mechanism open. Once we're at depth, we send down the messenger that puts, by putting your thumb on top of the straw, and up comes this. That's a history book. In this case, the last few hundred years of this lake's history. And then, we section it here. I'm going a quarter centimeter at a time. That's every time I go deeper, I'm going 2 or 3 years older in history. And in that mud is information. We're using information in that mud. And much of the things we look at, we don't look at fish because we don't find many fossils of fish, but we're looking at fossils of different organisms. And this is important because different species of organisms indicate different things. Some are found in acid water, some in alkaline water, some in cold water, warm water. And many of the things we're looking at are quite small. You wouldn't see them. We use what's called a plankton net if we have to go looking for them. This is we pull this through the water, and it filters out the water basically, and it keeps the big stuff, the relatively big stuff. The big stuff I'm talking about, you need a microscope to look at, and you capture it at the bottom here, and then you can actually find out what's living in your lake. And these are some of the things we look at. Things, for example, here in the middle, I have what I call water fleas, things like what scientific name is Cladostria. You've probably been by a lake or pond, and you see something maybe the size of a dot swimming around. Well, there are many species of those dots, and different species. Some live in cold water, some in warm water, and we can reconstruct it from these fossils. It's a bit like what archaeologists do, but we're doing it in lakes. I only have one picture of data. I figure I should show one picture of data. I know they're very hard to look at, but this is what it comes down to. This is going back in time, thousands of years on the left-hand axis here, and this is the percentage of different fossils. And all I want to show you here, some of the major fossils. What I want to show you is clearly something. For thousands of years, there was domination of this cold water species. Then over the last 100 years or so, we see a very, very big change in the fossils. And we can link that to climate warming, for example. So we can use this as like a paleothermometer. We use it for many other things, but that's more or less what the data look like. Now, the last 10 years have been very, very warm. And what's happening there is some of these ponds, some of these sites we work on are simply disappearing. And I just want to show you what I think is some dramatic photographs of what's happened in the last 10 years. Here is a photograph of one of the ponds I study up on Ellesmere Island with Marianne Douglas. This is a picture even before I was going there, in the top left here of a pond back in July in 1979. Here's the pond in August of 1987. It's gotten so warm, the evaporation has been so high, now these ponds are simply disappearing. They're evaporating away. This is a small pond. This is a bigger pond. This one's about the size of a football field. That's back in about 20 years ago. It was still a perfectly healthy pond, even late in the summer in August. This is what this pond looks like now in July. These whole ecosystems, these whole ponds are evaporating away. It's gotten so warm up there. It's still relatively cold to down south, but warmer than it used to be in the Arctic. So just since the 1980s, we've seen the water levels drop. We've seen temperature increase. We've seen ice cover decrease with warming. We've seen the water evaporating away, and we've seen with evaporation increasing, we've seen the water levels go down, and we've seen the salinity, the salt in the water increasing. And I use the analogy, if you had the same thing's happening up there, if you put a pot of soup on the stove and you put the lid off the pot and you put it on low heat, you'd see and taste two different things. You'd see slowly the soup level going down as it's evaporating. That's exactly what we see happening in the Arctic. The water levels are going down as they evaporate, at least in these sites. If you kept tasting your soup, it's getting saltier and saltier and saltier. That's because water is evaporating, but it's leaving the salts behind. I've been measuring with Marianne Douglas the salts in these waters for 20, 30 years. The salt levels have steadily been going up. So we know the ponds are simply evaporating away. And finally, you say, who cares? It's up in the Arctic. Who cares? I don't live in the Arctic. Well, what happens in the Arctic affects us all. It affects climate system. It affects ecology. We are intimately linked with the Arctic, not least of which, and there's many ways we're linked, not least of which is the big glaciers in the Arctic are melting. this what we call land-based ice, and they're going into the oceans, and ocean levels are going up. There was just a paper published yesterday. It was on the CBC and other things about how fast ocean levels are increasing. I mean, it's fast. We're talking about centimeters, but if you live by the ocean, it'll have an effect. So we are intimately linked with what's happening in the Arctic. So we shouldn't just pretend it's far away. It does affect us all. So that, in a nutshell, is what I've been doing for 30 years in 15 minutes.
All right, very good. Thank you, John. That was certainly a very good intro to both the problem of climate change and how you're starting to address that and measure it. So I'm being inundated by questions on Twitter right now, so I guess I should get right to those. I'll pick up right from where you left off, which was the melting of the ice caps and the glaciers up north. So we have a question from Lisa on Twitter, who simply wants to know, if the ice caps continue melting and cause the sea levels to rise, how will that affect the climate of countries surrounded by water?
Yes, it'll affect all countries as sea levels rise. When sea level rise, it's not so much a direct effect of climate, though it will affect it to some extent. One of the biggest problems with sea level rise is land is disappearing. So even places like, Charlottetown and places like along the coast of Canada, as sea level goes up, land is being flooded. And very importantly, when you get a storm, like a hurricane or a major storm, that water is going to go much farther inland. Now, this is definitely going to affect Canada as well, on the ocean side. What is really, really seriously going to affect countries is places like, for example, Bangladesh. These countries are very low in elevation. They're basically on swamp-type land, and they're very, very vulnerable. Or, for example, the small, what we call island states, these small island countries in the Pacific Ocean, as water level goes up, some of these islands may have to be totally evacuated. So the big effect is what we call extreme events and flooding, and that's going to be one of the biggest problems we have.
Okay. We've got a recurring question here from a few people. So in particular, Katrina from Twitter, Brittany, and Lisa again. And that is, can the effects that we're having on climate change be reversed, or are we only able to move forward with the impacts that our actions have taken?
Well, that's a very good question. We've been so slow in taking action. We are definitely going to see the effects of climate change. We're already seeing the effects of climate change, and we're going to keep seeing them. So now what we're talking about is to try and turn it around and bring it back. But that's going to take many decades to see that effect. So there's two things. One, we have to keep decreasing greenhouse gases for future generation, for our children and grandchildren. And also we have to get prepared for our own lives and the lives of people around us, of how climate is going to keep changing. There's already enough greenhouse gases now we put in the atmosphere. We're already seeing changes. We're going to see more changes. So right now we're talking about how to slow it down, mainly for the future generations coming, or for the young people in your listening. They will see more of it than I will, because I'm significantly older.
Mm-hmm. So if you just go ahead and close your slides there, we can see your whole image, if that's possible.
Do I know how to do that? Do I just close it like that?
Just close the...
That do it?
Yeah, perfect. Good. Now we got your full screen there. Good. Okay, so where am I here? So we have a question from Emily Weller at Bateman High School in Burlington. Are there any positive aspects? That is, will climate change benefit any areas of the environment on Earth, and how and why?
Yeah, there's always winners and losers, but when people have done these analyses, they have far more losers, but there's always some winners. So, for example, in some areas, I like wine, for example. In some areas, some wine growing regions will go farther north if the soils will support it, for example. In some areas, agriculture may move into an area that before it was too cold for that agriculture. But when they do the analyses, when they've done these various reports, there's always some winners, but there's a whole lot more that's typically lost. But that's true of some species, never mind just humans. Other species, some species will move farther north into what they before was too cold for them to survive. But there are winners and losers. But on balance, whenever they've done one of these analyses, the losers far, far seem to outweigh any winners that might happen.
Okay. So again, on that issue, a shout out to Class 7B from Macmillan School. Why is it that we can't fix the ozone? Or if we could, why isn't it being fixed? Like, what
The
actions would
the ozone Yeah,
yeah.
the ozone layer is a little different. I mean, there's some links, but the ozone layer was mainly it has some links to climate change. But most people, when they talk of ozone layer, is not so much in the context of climate change. It's in the context of ultraviolet radiation hitting Earth, and that came from the release of what were called mainly from the release of what were called CFCs, which were in things like spray cans, and in refrigerators and in air conditioners. They were banned after a so-called Montreal Protocol in the 1980s. And so slowly, in many parts of the world, the ozone layer is actually slowly recovering. It's not a straight line recovery, but many people would argue the ozone layer is sort of one of our more successful environmental stories. So, but it's got an indirect link to climate change, but that's almost like a separate problem. That's the other thing to think about with climate change. It's not just climate change is one of many problems humans are causing. And very often, I call it climate change and others like a threat multiplier. It seems most environmental problems are worse with climate change. So it's good to bring out the idea that it's not just climate change. We're adding chemicals, we're adding all sorts of things that are having other negative impacts.
Okay. So there's many gases in our atmosphere, and we have a question from Robert Bateman in Rita Collier's class, and he wants to know why do the greenhouse gases H2O and CO2 trap heat better than, say, N2 or O2?
Whoa, I'm probably the wrong guy to be asking. That's a chemistry physics question. That'd be a little tough for me to answer, but it's a very good question. I think you'll need another expert here too. But there's
Okay.
differences. There's certainly like methane, for example, is many times better trapper of greenhouse gases than even CO2. So there's very big differences, but that gets down to chemistry that is above my pay grade.
All right. Fair enough. Fair enough. So you kind of talked about it, but the whole branch of paleolimnology, that's basically what you encapsulated by taking these coring samples. Is that right?
Correct. Yeah. Limnology is the study of lakes and rivers. It's like the freshwater side of oceanography, or the inland water side of oceanography. And paleo is going in history. They do the same techniques in the ocean. They call it paleo-oceanography. So yeah.
Okay. Okay. Um, Let me see what I've got here. So we've got a question from Tyler Phillips at St. Peter the Apostle Catholic High School. And why do you say, he wants to know, why do you say that the Arctic is warming, but the Antarctic is expanding?
I don't think I said that. Expand, did I say? The Antarctic is also, large parts of it are warming as well, especially the Antarctic Peninsula. There's differences in the Arctic and Antarctic. For example, the Antarctic is one big continent, one big mass of ice, so things tend to happen more slowly there. The Antarctic is a series of islands with water in between them, so there are differences, and we tend to see things happening faster in the Arctic. But the Antarctic, I don't think I said it was expanding. I think maybe I said there's some differences between the two, but they're both under threat. But if you have like a big cube of ice and a small cube of ice, let's say, the small cube of ice, you'll see changes a lot faster because it takes a lot of inertia to start melting a big cube of ice. But there's definitely changes also happening in the Antarctic.
Okay, very good. So you mentioned long-term trends in global environmental change, and tracking this all the way back, hundreds of years. How long-term are we talking though? Like how long-term back can you probe?
Yeah, that's a very good question. It depends which method we use. Now, most lakes in Ontario, for example, we can go back about 12,000 years. And that's because before that was the Ice Age. And this is a good point. We're not saying all climate change is due to humans, because there are natural reasons for climate also change. We know that, really know that the changes we're seeing now, we can definitely link to greenhouse gas emissions. But for most lakes in Ontario, we can go back 12,000 years. That's simply because before that, the lakes weren't there. They only formed. Now, there's some parts of the world where lakes are much older, going back millions of years, and we can go back that long bit. But we need big cores. You don't have a little core like I was holding in my hand. You have big machines pushing down big cores. They're like ocean rigs and stuff like that. So, but in practical purpose in Ontario, about 12,000 years. Excuse me.
Yeah. Okay. So we got another question from St. Peter the Apostle Catholic School here. And this is a good one. How do you know that climate change is not just a cycle?
Yeah, it's basically from work, for example, that we do and many other people do. If it was a cycle, we would go in the paleo record and show that what we're showing now, there's nothing peculiar about it. We actually understand a lot about climate change. We understand definitely the sun is important. When we understand a lot about the sun and any cycles in the sun, like sunspots and stuff like that, we understand a lot of that. In fact, right now, the Earth should be getting cooler, and it's not. And we work with modelers, we work with many, many different scientists, and the overwhelming consensus of over 99% of the scientists working on it is you cannot get the warming we're getting without the human-induced greenhouse gases. And people say, well, how do you know greenhouse gases have increased? Well, we know that from a variety of sources. Other methods, not just the ones we use, but we use the Antarctic and the Arctic we've just been talking about. There's other ways to get back at the historical record. One is ice cores. You have several kilometers of ice on Greenland and in places like the Antarctic. And that's also a history book going back much farther than 12,000 years. And scientists in these, like the Antarctic ice cores, go back in time and they can go, this is like the 1700s or 1,000 years ago or 500 years ago. And they can look at bubbles that are entombed in the ice. And they can analyze how much greenhouse gases in those bubbles. Those bubbles are capturing what the atmosphere was like 100 years ago, 200 years ago. So they can show how CO2 has changed over time. Not only that, but they can use methods to pinpoint if that CO2 was from natural burning or from coal burning or fossil fuel burning by using isotopes, for example. And they can actually pinpoint that's from coal and fossil fuel burning, and we can link it to our climate records. We can show this is not part of some cyclic cycle. We can show this is something very aberrant, and we can link it very clearly to the effects of humans. So that discussion, that the data for that are gone. It's not a natural cycle. There are natural cycles, and we understand them. There's hundreds and hundreds of scientists working on that side. It's not a complete mystery. But what's happening now is not part of the natural cycle. There's so much data out there now that we know we have to take action.
Right. Okay. Good. That sounds pretty conclusive then. So we're running a bit short on time. Let's see if I can fit in one or two more questions. And this comes from Daniela, who's a grade 6 student at Regal Road Junior Public School in Toronto. And she wants to know, is there anything that she or her community can do to stop this issue? Like what are one or two things that the students may be able to help with?
Well, there's lots we can do. It's very easy. When you have a big problem, it's very easy to say, what will one person do? But that's the only way we solve these problems, one person at a time. And so whenever there's a way of reducing your own greenhouse gas footprint, as we say, you should do it. And that includes maybe you don't need the house as hot in winter, put on a sweater, put on more clothes, lower the heat. Maybe you don't need the house as cold in summer with air conditioning. That's a big use of things. Maybe you don't need to drive the car everywhere. Go for a walk, ride a bike, use public transportation. There's all these little things we can do. We can use better products. We can be more careful of the products we buy and how much greenhouse gases we used in them. And of course, all your listeners will eventually be voters. We live in a democracy. And we have two powers. People say I have no power. We have two powers. We have power of our wallet, where we decide what we buy and how we spend our money. And we have power of our vote. And people, should look very carefully when they become voters and they start voting for who's going to be the next leader of the country and of the province and the municipality, that environmental issues are one of the things they vote on because it's going to affect them and their children and their grandchildren. And not just looking at short-term financial gains, we have to start using our votes and our wallets to make the decision we choose to make. But it's very easy to say, there's nothing I can do, because the reason we're in a problem is because everyone's kind of saying there's nothing I can do. It's not just individuals. We have whole countries saying there's nothing we can do unless everyone else does it. Someone has to start. Someone has to show leadership.
Right. Okay. Well, I think that's a very inspiring note for us to end on, as we're fresh out of time here. So I'd like to say thank you again to all of our live stream viewers. You certainly sent in lots of questions. I love to have more time to get to them all. And of course to you, Dr. John Smol, for taking the time to answer those questions and to share your expertise with us today. Thank you very much.
Thank you very much. Happy to be here.
Okay, before I sign off, I'll just give a quick heads up for next week, which is Canadian Agriculture Literacy Week, and we have a PIR live event doubleheader, actually on Thursday, March 3rd. That starts at 10 a.m., and then it also starts again at noon, when we'll talk about climate change and agriculture with Dr. Romila Verma and Dr. Liette Vasseur from the Environmental Sustainability Research Center at Brock University. So that will certainly be interesting, and follow on what we've heard from today from Dr. Smol. So bye for now, everyone. Until then.